Welcome back, ladies and gentlemen. Today you finally get to know why I have a picture of a mole on the slides of this unit, and today is the day we will learn about moles and how they play a role in atomic conversions. Now, if you remember, I mentioned back when we did dimensional analysis that this was going to be an important concept that you need to be able to use later on. Well, that later on is today. So let's dive on in. Your learning targets today, hopefully by the end of this video, you will be able to explain the concept of the mole, Avogadro's number, and molar mass. You should also be able to perform conversions between moles, atoms and molecules, and grams of a given substance. This will take some practice, and this will take some time, but once you get the hang of it, it's pretty straightforward on how to do this. We have three key vocab terms for this particular unit: mole, Avogadro's number, and molar mass. So when I talk about the mole, I'm not talking about, the little furry thing that lives under the ground and is blind, or the thing that's on grandma's face. What I'm talking about is the SI unit for the amount of a substance. And when you think of a unit for the amount of a substance, think like a dozen, right? If I have a dozen eggs, I have 12 eggs. If I have a dozen laptops, I have 12 laptops. Well, when I have a mole of a substance, I have the same number of those things. Now, the properties of those individual things can differ, like eggs and laptops, but I have the exact same number of them. So I want you to think about that. Now, the term mole originally came about as the amount of substance that contains the same number of atoms as 12 grams of carbon-12. And they found that out to be a really, 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 really big number. And that number was actually Avogadro's number. And it's equal to the number of atoms or moles in exactly 1 mole of a substance. It just happens to be 6.022 times 10 to the 23rd atoms per 1 mole. And this is used for atoms of hydrogen, helium, lithium, mercury. It's also used for molecules. There's 6.022 times 10 to the 23rd molecules of water in 1 mole of water. Now, this can be used as a conversion factor. If you remember, conversion factors it's the same amount of something, but it's in 2 different units. It's the same here. 6.022 times 10 to the 23rd atoms is always equal to 1 mole, so we can use it as a conversion factor. If I look at the diagram here on the right, I have a mole of carbon and a mole of copper. It's the same number of atoms, but the mole of copper has a mass of 63.5 grams, whereas a mole of carbon only has 12 grams. And that's because the copper atoms are bigger. They have more protons and neutrons than carbon atoms. Now, another term that we need to understand is a term that's called molar mass, and it is the amount in grams of 1 mole of an element or compound. So we're not talking about the number of atoms, but we're talking about the amount in grams. The molar mass increases as you increase an atomic number, as each particle contains more protons and neutrons, and thus the atom has more mass. These numbers are the numbers that you find on the periodic table. If you remember, in our previous lesson, we talked about average atomic mass. The average atomic mass being the weighted average of all of the different isotopes of a particular chemical element. Well, here, those particular molar masses are also the same as 1 mole of a substance. So we can use those as a conversion factor. So now we have 2 new conversion factors that we can use. We can go in between atoms and moles, and we can go in between moles and grams. Atoms and moles is always Avogadro's number, and grams and moles is based on the information found on the periodic table. So you'll see what we mean here in just a moment. Now, the molar mass is easy to see. If I look at the periodic table, I know that the molar mass of hydrogen is 1.007. I know that the molar mass of, I'm looking at a periodic table far away, so I apologize. Chlorine is 35.45. But what about the molar mass of compounds? Well, molar mass is summative, meaning that if you have a compound, you add the molar masses together to get the molar mass of the compound. So, if I want to know the molar mass of lithium chloride, LiCl, it's simply just the mass of lithium plus the mass of chlorine. So the molar mass of lithium is 6.939. I add that to 35.453, and I get my molar mass for lithium chloride, 42.392 grams per mole. So again, the properties of that are additive. Now it gets a little more complex if we use subscripts. Subscripts, the little numbers next to the elements, indicate multiple atoms, so we must include those in our molar mass. So for example, if we use calcium nitride here, Ca3N2 means that I have 3 calcium atoms, so I need to take the molar mass of calcium times 3, plus the molar mass of nitrogen times 2, and then add all of those together. Does that make sense? So we have 3 calcium atoms, so we need to take the molar mass of calcium 3 times. Same thing with nitrogen, since it happens twice. We add all of those together, and we get 148.26 grams per mole. Now, sometimes when you look at a chemical element or a chemical compound, what you'll find is that there are parentheses or brackets around parts of it. And you need to think about the distributive property of math. So if I look at the example here, calcium nitrate, CaNO3 2. Well, I've got 1 calcium, so that would be the molar mass of Ca, 40.08. The 2 distributes to both the N and the O. So here I have 2 nitrogens and 6 oxygens. So if you see it within a brackets, think like the distributive property of math. That 2 goes with the N. That 2 also goes with the O3. Remember, 2 times 3 is 6. So I have 6 oxygens. So my total molar mass is 1 calcium plus 2 nitrogens plus 6 oxygens. In this case, 164.1 grams per mole. Okay? So again, I'm covering a lot of information here. This will be something that we spend quite a bit of time on in class. So here's my visualization of how we can use the different conversion factors we've talked about as, well, conversion factors. So here I start with what I know and I follow the arrows to get to where I'm given. I start with what I know and I follow the arrows to my unknown. So for example, if I'm given grams and I have to convert to moles, so I'm given a problem that says take this much in grams, convert it to moles, I have to use the molar mass. Well, remember, the molar mass is found on the periodic table, so you calculate that and use that as a conversion factor to solve for the amount of moles. If I have atoms, molecules, or particles and I need to go to moles, I use Avogadro's number and do the conversion that way. If I have to go from atoms, molecules, and particles to grams, notice that there's not an arrow that connects them directly. So I'm going to have to convert atoms, molecules, or particles to moles using Avogadro's number, and then use the molar mass to convert the moles that I get into grams. Okay? So I know this seems a bit complex, but as we go through some of these practice problems, I think you guys will understand how this works. So let's look at this first practice problem. How many moles of silver are there in 3.01 times 10 to the 23rd atoms of silver? Again, just like we've done with every math problem in this class, break it down into your given and break it down into your unknown. The given in the problem is 3.01 times 10 to the 23rd silver atoms, and my unknown is moles of silver. So I'll use the mole wheel to find the correct path. Well, I'm given atoms of silver, so that goes on the top of the first step. As we do with dimensional analysis, we multiply it and draw a fraction line. We know that that unit, atoms of silver, has to go on the bottom of the next step. I know that there's a direct conversion between atoms and moles based on my mole wheel, and that is that 6.022 times 10 to the 23rd atoms is equal to 1 mole. So Avogadro's number goes in the bottom, and then 1 mole goes on top. My atoms of silver cancel, leaving me with just moles of silver, which is what I want for my unknown. And now I just do my math and solve by plugging that into my calculator. One thing I would recommend, since we are using exponents, is to make sure to use brackets or parentheses around stuff that you are dividing, because otherwise your calculator is going to calculate it wrong and you're not going to have a good time. So when we solve, we get our answer. Remember, the number of significant figures in our answer is the same as what we start with when we do a dimensional analysis problem. So 3.01 has 3 significant figures. So we're going to do 0.500 as our answer, and that's 0.500 moles of silver. Now let's try some problems together. So let's take a look at this problem. How many moles are there in 42.3 grams of calcium? Well, what's our given? Well, in the problem we're given 42.3 grams of calcium. And then our unknown, our question is asking how many moles of calcium do we get? So we start with what we know, 42.3 grams of calcium. Again, we're doing a dimensional analysis problem here. The unit grams of calcium is on top of the first step, so that has to go on the bottom of the next step. Now, looking at our mole wheel, is there a direct conversion between grams and moles? Well, yes. I use the molar mass for this. So we're going to have moles of calcium. This information is found in the periodic table, so we look at our periodic table, and for every 1 mole, the number that's on the periodic table always goes with grams. So we're going to have 40.08 grams of calcium for every 1 mole. My units of grams of calcium cancel, leaving me moles of calcium, which is good because that's what we want for our answer. So let's plug into our calculator and solve. We're going to take 42.3 and divide that by 40.08. We need to round to 3 significant figures based on our given. So it's going to be 1.06 rounding up moles of calcium. There we go. Simple enough. So again, find your given, figure out what your unknown is, do your dimensional analysis, plug your equations into your calculator, and solve. Let's try a few more practice problems just to make sure we have it. This problem asks, how many grams are there in 1.46 times 10 to the 23rd atoms of potassium chloride? Well, what's given? .56 times 10 to the 23rd atom. And since we haven't talked about nomenclature yet, this is something that I would give you. And potassium chloride is KCl, just so you know. So you have this many atoms of potassium chloride. Our unknown is grams of potassium chloride. So again, we write what we know. 4.56 times 10 to the 23rd atoms of KCl. Okay. Whatever unit's on top of the first step goes in the bottom of the next. Now, we need to go from atoms to grams. Is there a direct conversion between atoms and grams? Well, no. It says we have to go through moles. So the first thing we need to do is take our atoms and convert that to moles of KCl. And if we remember Avogadro's number, that's 6.022 times 10 to the 23rd atoms of KCl for every 1 mole. Now we're not done yet because our unknown is in grams. So we need to convert, we need to go another step. Whatever unit's on top of this step goes in the bottom of the next step. And then I need to think, can I convert moles into grams by looking at my mole wheel? And the answer is yes. Right? Grams to moles is always found in the periodic table. Now we're not just given one element, we're given 2. So we need to take the molar mass of K plus the molar mass of Cl. The molar mass of potassium is 39.10 grams. Then we're going to add that to 35.45 grams. So let's do a little bit of math here first. So my molar mass of potassium chloride is 74.55 grams per mole. Okay? 74.55. So again, what you'll notice here, and this is just for these types of problems, you'll see some different types of problems later on, but mole is always 1, okay? At least for right now. Now that will change a little bit later on. So let's take a look. Our atoms cancel, our mole units cancel, and we're left with grams of KCl, which is good. That's what we want our answer to be. So you can do this a couple different ways. You can multiply across the top, then divide by what's on the bottom. You can divide this, and then whatever you get out of that, then multiply it. However you want to do it is fine. Just make sure you're putting things in brackets. So I plug all of that into my calculator, and I should have 3 significant figures in my answer. So my answer should be 56.5 grams of KCl. Okay? So that was a little bit longer problem, but again, the concepts are still the same. Start with what you know. Work your way using the mole wheel until you figure out where you need to go based on what is your unknown in the problem. You may have to do a little bit of molar mass calculation to figure that out, but I think you guys will be able to handle that. It's pretty straightforward concept. All right? And again, we'll spend quite a bit of time in class working on these throughout the school year. So hopefully you have a little bit better understanding of the fact that moles, molar mass, and Avogadro's number are all units of measurement that help us understand how much of a certain chemical is present. And the fact that we can make conversions between all of these different values using the mole wheel, which provides an easy way to determine what conversions to use based on your given and your unknown. Hopefully you understand a bit more about these concepts. We'll dive a little bit more into this in class and definitely spend some time on it, as it is an important concept in chemistry. Wish you guys the best of luck, and as always, let me know if you have any questions. We'll talk to you later. Bye-bye.